Hi 107 fans, I'm going to show you another two-trait cross. This time they're not going to be both dihybrids. They'll be a combination, sort of like what I showed you guys in class. So this would be fair game for something on the exam. If I gave you, we'll use the same letters that we used in class. If I gave you a genotype, like so, one parent times another parent. What are all the possible offspring these two parents could possibly have? So the first thing we need to know is how many different types of gametes could each of the parents make to set up our square. So again, this little t could go with this big P. So we could have little t, big P. This little t could go with this little p. Uh-oh. P didn't show up. Okay, there we go. This little t with this little p. We could have this little t with this big P. And for the last one, we could have this little t with that little p. Okay. And what we notice here is that these two are the same, and these two are the same. And the Punnett square is giving us probability. So we don't actually need to look at genotypes that are exactly the same. We can, but it just would take you a lot longer to fill out your Punnett square, and you're going to end up with the same answer anyways. So I'll illustrate that in just a second. So what are our other options? What is this parent? This parent can do big T, big P. I'll put them up here. Big T, big P. We could also do little t, big P. And then he could do big T, big P. Seems familiar. And we could also do little t, big P. Again, seems somewhat familiar. Right? This guy is the same as that guy. This guy is the same as that guy. So these are all the possible gametes. So really, if we're looking at a square, we don't care about the extras, right? Because we could do them if we added them in the square. We'll illustrate the beauty of probability in mathematics here. Okay? But we're going to focus on what happens in this part of the square. Okay, so again, we're going to bring little t over, little t over, little t over, little t over, big T down, big T down, little t down, little t down, big P over, big P over, little p over, little p over, big P down, big P down, big P down, big P down. Okay, and so these are all the possible genotypes that we can get from these parents. Now, if we fill in the other squares that I told you could leave off, right? If we brought this little t over, and little t over, and big P over, and big P over, and then we brought big T down, and big P down, and little t down, and big P down, you can see that this square here is exactly the same as this square. And this square here is exactly the same as this square. Okay? And if we fill out the rest of the squares, you're going to find the exact same thing is happening. Big T, little p, big P, little t, big P, little p. Right? These guys, this one looks just like this one. This one looks just like this one. Okay, and when you're looking at probability, let's just finish this out here. Okay, so little t over, little t over, big P 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 over. Oops, I forgot the last layer. Okay, big T down, big P down, little t down, big P down, big T down, big P down, little t, big P. Okay, once again, you can see this one is the exact same as that. This is the exact same as that. And again, if you're going to make me do this, right, this is little t, big T, big P, little p, little t, big P, little p, big T, little t, big P, little p, little t, big P, little p. Oh my gosh, can't even read it in the corner. Okay, and what we see, again, another color. This one is the same as that one. This one is the same as that one. So if you count them all up, right, we would have in just our original square that I said is really all you need to draw because the rest are duplicates, right? We have a 1, this guy, a 1 out of 4 chance of getting little t, big P. Okay, so there's 1/4 chance of that, right? There's 1/4 chance of this guy, 1/4 chance of this guy, and 1/4 chance of this last guy, which I have nowhere to draw. Okay, if we add all the rest of the guys in, you're going to see that if we count all the guys that look just like this guy, 1, 2, 3, and 4. 4 out of 16 look like this one. Well, what is 4 out of 16, right? If we use lowest common denominators and all that good stuff, right? 1/16 goes down, 4/16 goes down to 1/4. Well, that's what we figured out just from doing the small set. Because by probability, right, it's how many squares out of 16. So you don't have to do all of them if you have gametes that repeat themselves. Like this one and this one are the same, and this one and this one are the same. That means you don't even need to use those. You don't need to do those. So this whole part of the square is a gigantic waste of your time. Because by probability, 4/16 is the same exact thing as 1/4. So you only need to represent the gametes one time if they're duplicated. So I hope this helped. I know this is a lot of scribbling, so try some of these at home and see how you do. And thank you again for listening.